We are going to talk about center mass and moment of inertia. Center mass is something we just kind of flew by, and moment of inertia is something that I just introduced at the end of the last lecture. We're going to have more on today in lab. So this is stuff that is like the British spelling of center there. This is stuff that is intrinsically calculus. So the equations that we had from general physics, the center mass is the average position of the mass. And so if you're going to calculate it, which we never did in general physics, you add up a weighting factor for each mass. What's the weighting factor? Its position. So you have each mass times its position, add those up, and then divide by the total mass. It's exactly the same idea as finding the average score on a test. So if I had, let's say, 100 tests, I would say, okay, I had one student with a score of 99, and one student with a score of 93, and one student with this. I add all those up and divide by the total number of students, and I have the average score of the test. Or I can make it a little simpler and say, well, I said one student had this score. I actually had 7 students that had a score of 99. So my weighting factor would be 7 times 99. And I had 3 students with a score of 95, so I have plus 3 times 95. And then at the end, I divide by the total number of tests again. And that's what we're doing here. If I have mass, if I have these two masses here, I'd say, okay, the center of mass is, I need to choose a reference point for position. So I might say, I'm going to use the center of this one as my reference point. Right? And usually a problem will give you a reference point from where to find it. Then I say, okay, I'm going to have this mass, 5 kilograms, times its weighting, times its position, 0, plus this mass, 5 kilograms, times its position, let's say that's 10 centimeters away. So I have 5 times 0 plus 5 times 10, then divide by the total mass, which is 5 plus 5, 10. And I would end up with 5 centimeters. And that's what the center mass is. Now that's really easy with discrete things.
How'd you find that last part?
I'll write it down. So my little example is oh goodness gracious, great balls. And I'm just using cardinal numbers because that's what's stamped on them. I'm using 10 centimeters because I approximated it. It's clearly not an exact number. And so then to find the center of mass, this means when it has summation, subscript I, mi, xi, that just means you're summing over all of the objects present. And then divided by sum over I, mi, which literally means m1, x1 plus, what was that?
What does I mean?
I means whichever item you have. So you're going over all of the items. So that's why I have m1, x1 plus m2, x2 because I had 2 items. And so I was 1 and then I was 2. So this is object 1, this was object 2. Mm-hmm. And so this had mass m1 in position x1. This one had mass m2 in position x2. And then I had to sum through all of my items, so that's why the summation over all i's of mi, xi became m1, x1 plus m2, x2.
Okay.
And then on bottom, sum over all the mi's, what's that going to be?
M1 plus M2. Then all your m's cancel out, you're left with x.
Because all the m's are the same, they do cancel out. I'm actually going to put the numbers in, but that would be the quick, smart way of doing it. So I'm going to have 5 kilograms times 0 plus 5 kilograms. I know my first kilogram looked funny. Times 10 centimeters divided by 5 kilograms plus 5 kilograms equals 50 kilograms times centimeters over 10 kilograms equals 5 centimeters. And because I was playing fast and loose with sig figs, I just left it at 1. So that's how that calculation goes in an algebra base. Likewise, moment of inertia the thing we talked about last class period. I said it's mass times the radius from the rotation axis squared. And so in this case here, I don't have rotation. I can't really do a definition of that, right? But I can grab one of these chairs. I, of course, should have brought out my wheel, but I didn't think about that beforehand. And so I put one there, one here, and then I rotate it. Where is the R measured from in that equation?
Center of mass.
Not the center of mass.
Moment of inertia.
I is the moment of inertia, but there's a location that I need to sum it about, and you were saying something I didn't hear.
In between them?
It's somewhere in between them because of where I laid them out. It wouldn't have to be in between them. It is going to be from the axis of rotation. So what axis is this rotating about?
What?
The one that comes down the center of the chair, right? And so I'm going to measure my R's. R1, can you guys all see me here? R1 is this distance, and R2 is this distance. They're both going to be positive radii from that center. And so in this case, I might have, let's say, 5 and 10, just something like what I did. So in this case, I have, this M's are the same, but I have R1 is equal to 5 centimeters, R2 is equal to 10 centimeters. And then applying that equation, I should change colors for this part now, shouldn't I? Blue it is. Then I'm going to have I is equal to sum over MIRI squared is equal to 5 kilograms times 5 centimeters squared plus 5 kilograms times 10 centimeters squared. And 5 times, well, 5 squared is 25. 25 times 5 is 125.
Yep.
I have 125 kilograms times centimeters squared plus,
500.
yeah, 10 squared is 100. 100 times 5 is 500. I try to encourage people to do math in their heads and not rely on the calculator when you can. And so I, fortunately, could add these two numbers together as well. 625 kilograms times centimeters squared is the moment of inertia. That's not the SI units, right? What would the SI unit be? Well, what should it be?
Meters squared.
Kilograms times meters squared. So Oksana was talking about converting units. How do I convert this to get it into kilograms times meters squared? Okay, there's 100 centimeters a meter. Which needs to be on top?
Where?
That's right. Both of you are hitting the right topics. Which one needs to be on top, the centimeters or the meters?
Centimeters going to be on the bottom.
So you need meters squared, centimeters squared, and 100 squared.
Just square the whole conversion factor. It's the same thing.
That works.
You've got to make sure you would have 100 centimeters squared, not just 100 centimeters squared.
100 square, 100.
Oh, yeah.
10,000.
Yeah, no, I know what you're talking
Yeah. Okay, and so yes, that's going to be 0.0625 kilograms times meters squared. So that's the way that we have for Physics 151 to do it. You know what Physics 151 is going to do for anything more complicated?
They won't have anything.
They're going to look at a table.
Oh, okay.
There's a table in the textbook. Here's the moments of inertia. They're going to look at the table, and that's what they're going to do. Why? Because life is not so simple. I was treating these masses as if the masses had a specific location, but they didn't really have a specific location. The masses had volume. And so if your masses have volume, well, then you have to add up these equations for every little piece of mass. What do we call the process of adding up for every little piece of mass? Integration.
Oh.
We're going to have to integrate. That's how we add up a continuous distribution. And I said for every little piece of mass, what that means is we're going to be integrating position, in this case, squared if it's moment of inertia, or not squared if it's center mass, times dm, the little tiny piece of mass at that position. So we're going to have integration instead of summation. Remember, the symbol for summation, that is a capital S in Greek.
Sigma.
The symbol for integration is a capital S. Anybody ever made that connection?
No.
So what we're going to do is we're going to take this and we're going to make x center mass is equal to integral. See, that's a S?
Yeah.
And then I'm going to put the x first, dm. dm means a little tiny piece of mass divided by the integral of dm. And the moment of inertia, what's the moment of inertia equation going to be?
The integral of r squared dm.
Now, I usually put an r perpendicular there just to make sure we remember it's the radius going from our axis of rotation that's perpendicular to the axis of rotation. Remember in class yesterday, I was like, I'm holding like this or whatever. Where do you measure from? Just from that axis. You don't go like this or like this. The perpendicular distance from the axis. So,
What about
go ahead.
I? Okay, so like, how did you get R D and
Okay, r squared. Where's
your next?
Summing over each piece of m, dm. There was no x here, right?
Okay.
So, of course, I have slides to show you just those equations. Haha, surprise. But then I have where dm equals. We got it. How would I integrate over dm's? If you think about that, it starts to get really confusing. Well, what we have is we have mass distributed over region. And so we have the idea of, do you know what rho looks like? That. Do you know what it stands for?
It used to stand for momentum, but apparently that's not true.
No, P stood for momentum.
I was taught that rho stood for momentum a long time ago.
I was never taught that, thankfully.
Anyway,
Okay.
what does rho stand for? Not momentum.
Rho stands for density, the mass per unit volume.
Yeah, that makes a lot of sense.
So if rho is the mass per unit volume, then mass must be rho times the volume. Volume is spatial dimensions. We can work with that. And so we have dm is rho dv. And of course, especially for my friend David, this brings consternation. It does. Because what is dv?
Volume.
Changing volume.
For calculus purposes, if we're working in Cartesian coordinates, we define positions by x, y, and z, right?
Yes.
So dv means some very small piece of volume.
Right.
And with Cartesian coordinates, we say, okay, we're going to make a cube for dv. And that cube is going to have ds. I said a cube, but it's actually not necessarily equal lengths on all sides. It's going to have dx on one side, dy on one side, and dz on the other, on the third.
Where is dv?
And so what is dv going to be then if it's dx by dy by dz?
Oh, now you.
No, that was, what's the equation going to be for dv?
Well, obviously the area times dx.
I'm being really specific in this mostly because I don't think David's actually had this in class. So there's my dimensions. And so the volume contained by this is what we call dv. And how do you find the volume?
Based
on integral.
Yeah, base times width times height. So that's just going to be dx, dy, dz.
Right.
And likewise, once again, I said consternation for David because that means when I do an integral, what's my variable of integration?
You have 3.
I have 3. I have a triple integral.
Yes.
Yes.
Or You could do that thing down below.
Or-
I and DZ is the area.
Notice the word often.
Yes.
Often we can simplify this to dV is equal to cross-sectional area. Cross-sectional area means the area that is normal to the variable that we're going to consider times dx.
Perpendicular.
So if x is going this way, the area is the cross-sectional area measured in this direction. So often we can use that to simplify our integrals. And anytime you can simplify, you want to do that. Right? Don't be like, oh, I've got to do this the hardest way possible. That's not right, the right spirit. So let's just do some problems. Find the center of mass of a uniform rod of length L. What does the word uniform mean?
The same throughout.
Okay, the same throughout. That means the density is constant everywhere in that rod. The mass per unit volume is constant everywhere. This rod also, just by the definition of rod, it's going to have the same diameter as you go all the way down the rod, which means that the cross-sectional area will be constant. So we can use that simplification. So we are going to have dm is equal to rho dv, right? That's always true. Is equal to
the unit vector.
area times
Row area dx.
rho dx.
Is lambda in this case the unit vector?
No, it is not. So lambda is introduced as what this equals, what rho times area, just so it's one less symbol to write as we go through our work.
How does that equal mass over length?
Well,
Or is that into something else?
let me just write it out instead of explain it. So density is defined as mass over volume.
Yes.
And so if I take density and I multiply it by area,
Then you've taken out the depth and the height and you're only left with length.
yes. But that's an important question, right? You should be questioning things. You shouldn't just be saying, sure, whatever you say, that's not the way to learn. That's the way to be indoctrinated, maybe solve some problems, but not understand. Okay, so why do I have that equation that lambda is m over L, the mass per length? We call this the lineal density, by the way. Lineal density because it's the mass per length, whereas rho is technically the volumetric density, the mass per volume. We have this because if I tell you the mass of the rod, mass is, I don't care for this problem, I'm doing everything in symbols. And I tell you the length of it, then you immediately can calculate if it's a uniform rod what lambda is. If it's non-uniform, things are going to get more complicated. So here it's uniform because it is our first problem of this type.
So we are going to do non-uniform stuff.
Sure, it can show up on your next test. So I have what dm is. dm is going to be lambda dx. And so now I can do my calculation for the center mass. I'm calculating, the problem says, for a uniform rod, the mass is evenly distributed throughout the rod, so blah, find the center mass. It doesn't say what to use as a reference point. What point would you like to use as the reference point?
Can I just say the origin?
Yeah, I would too, right? This picture is drawn, so there's the origin. So there's where x equals 0. That's what I'm going to do because it's going to make my life easiest. So now I do my integral of writing the whole thing out. It was x dm over integral of dm, right? Mm-hmm. And then dm was lambda dx.
Yes.
And in this case, lambda is a constant.
So you can cancel out the lambdas and
This is actually true, but be very careful with that. Because, for instance, you couldn't cancel out x's, right?
no.
So be careful with that. I've seen people try to do that where they have the integral of x squared divided by integral of x, and they say, oh, well, clearly that's just cancel the x's. integral of x over integral of 1. No. Not, yes. So you can, because they're constants, bring those out. Lambda is, yes. For this problem, because of the word uniform. If it didn't say uniform, then lambda wouldn't necessarily be a constant. What are my limits of integration? You always need to determine the limits. I know this is going to sound crazy. We're not in calculus class here. All of our integrals have limits.
Would it be x plus x?
Well, what's our starting?
L.
0 to L.
0 to L. We're starting at 0 and ending at L. Yeah. Yeah, because the picture shows the length L. So our lambdas cancel, so it doesn't even matter what the mass of this thing is or the area.
Okay.
And we have, what's the integral of x dx?
X squared over 2. And the integral of dx is 1.
It's actually x.
You're right.
Now that we're outside of integrals, I still can't cancel. I have to apply the limits first. So if I apply the limits,
L squared over 2 minus 0 squared over 2.
right, you have to remember to do the upper limit minus the lower limit. Now, the lower limit in these cases is just going to give a 0 on top and bottom, but still being explicit. Now, of course, those are zeros, and I just cross them out. They're not canceling. They're zeros. And I have L squared over 2 divided by L.
So that's going to be L over 2.
At this point, you probably are all saying, you know, I'm not some kind of idiot. I could have told you the center of mass for a uniform rod is its geometric center. Right? This was a first problem. Notice what the next problem is.
Same with the pivot random.
Find the moment of inertia. We're going to use the same stinking rod, and now it says pivot about a random point P, a distance D from the end. Oh, Lordy, we made it a lot harder. Yeah, we did.
Well, unless you start from the 0, then that cancels out. Start where it equals 0. Take the moment about
that's
L,
what it is.
or whatever it's called.
That's D, and then L is the whole thing.
Right, L is the whole length.
And the center.
Not torque, but the moment of inertia.
How's that different again?
Well, we haven't seen this equation yet in this class. You might have seen it in statics. But the net torque is equal to I alpha. If you look at the YouTube tutorials that I have where I work out problems and stuff for you, you'll see that somebody's cracking on me. He's like, you shouldn't write the equation that way. And he's kind of right. Because moment of inertia, notice I have the net torque vector. I have alpha vector. And it looks like I is going to be a scalar. But moment of inertia is not a scalar. Moment of inertia is what we call a tensor. What does that mean is a very good question. Okay, so you have scalar, vector, tensor. A tensor is a multidimensional vector equivalent. So we represent tensors as matrices. And the moment of inertia tensor is a 3x3 matrix. So you have IXX, IXY, IXZ, IYX, IYY, IYZ, and so on.
It's a multi-dimensional vector.
Yeah, well, in our case, we're doing a two-dimensional vector, or it's got. So it's a 3x3 matrix. Tensors can get much more complicated than that. So that's why he's cracking on me because.
What's a symbol for a tensor?
I don't even know. I think a tensor is drawn like this with a two-sided arrow on top.
Interesting.
And so, if I did that, then I could say, oh, no, I'm totally right. But what we do for this level of class is we talk about the principal axes. Now, this is something I totally didn't come to talk about, but it's so fun. You take an object like this. It has three principal axes, three axes where you're going to have that tensor. If you choose the right coordinate system, the tensor will have all of the non-diagonal elements 0. So it just has IXX, IYY, IZZ. All the IXY, IXZ stuff, all of those are zeros. And the way you do that with this is simple to see. You have, based on the symmetry, one of the principal axes is this direction, one of them is this direction, and one of them is this direction.
Why isn't it diagonal from one corner to another?
Just because this has the planar symmetry, that's what defines this, the symmetry. Okay, so now, interesting thing. If I do these, one axis is rotating like this. One axis is rotating like this. One axis is rotating like that. If you look at those three axes, which one has the mass farthest from the axis of rotation?
This one.
Yeah, this one does, because you have out here and out here. You have that diagonal. Whereas if you're doing, for instance, this way, you don't have the diagonal, you just have this dimension. So that means this has the largest possible R's, and thus the largest moment of inertia about this axis. Which one has the smallest moment of inertia? If you go like this. So we have the largest and the smallest. Each one of those are stable. If I throw this and I rotate it correctly about the one with the smallest moment of inertia, it rotates stably. If I rotate it about the one with the largest moment of inertia, just do it this way, it rotates stably. If I do it about the one in between, which one was the one in between? That was this way. Yeah. If I do it this way,
Okay.
it tumbles.
It tumbles.
It tumbles. What it did is it broke it down into rotations about the other two axes as well. And so you have to be absolutely perfect to keep it from tumbling.
Okay, I was about to say, but it should be possible to keep it there, right?
Yes, if you're absolutely perfect, yes.
Okay.
But if you're not absolutely perfect, you have a little bit in the other ones, and it will shift back and forth. Whereas, so that's just a cool thing to know. We're not going through any of the details of why that is, right? Because that gets a little complicated. Just coming back to the notation, that guy cracking on me for writing my notation that's not technically correct. And I mean, I recognize it's not technically correct, but it's functionally correct for us. So this is the relationship that you asked about. We haven't covered that yet, but we will. The net torque is I alpha. That is the basis of rotational dynamics. Well, in the reading, you are past there. I was supposed to have lectured on that on Wednesday, but instead I went over the test. So that's something we're going to cover in lab today. That's why we're not doing the normal lab to make up for that. Well, there's going to be a little experimentation as well. It's going to be a hybrid.
But the quiz thing wasn't due today, right?
I'm not going to grade the quiz, or it's not going to count toward the grade, I should say. It's
No,
automatically graded.
I mean the quiz, what's it called? The pre-quiz.
The pre-lab quiz.
Yeah.
Yeah, I'm not going to count that toward your grade.
So we're not doing it.
You do not have to. You can. It's still useful, beneficial for learning, but it's not going to be part of your grade. All right, so back to this. All of that last 7 minutes brought to you by one question for Andy. I just couldn't let it go. So we are trying to find the moment of inertia about this axis that's arbitrarily set. What's the equation for finding the moment of inertia? Let's get that out here first. I is equal to what?
Sum of
M equals 0.
The integral
the integral of r squared dm.
Perfect. If I put you guys together, you've got it perfect. And I assume, you each had it in your mind, and somebody says one thing, that was, oh yes, but we have to modify it with this, and yeah.
Do we really need to put the perpendicular thing there?
Do we really need to? If you get to something that is with, for instance, cylindrical coordinates, yeah, you're going to be confused if you don't put perpendicular.
Okay. Do we deal with cylindrical coordinates here or whatever?
Yeah, we do.
I should not have taken this class. Shoot, I said that out loud.
All right.
Carry on.
So there's my equation. What is dm?
dm is lambda.
X.
Once again, putting you guys together.
Yeah.
Lambda dx, because we have the uniform cross section. Now I have to be a little bit anal. This is true if the rod has a very small diameter. If it has a big enough diameter, well, then you do have some variation, based on how far you are, and then you come out one radius and use the Pythagorean theorem to find what the R perpendicular is.
Right.
So if it's very thin, this is correct. If it's a thick rod, then it's going to be a little different. And so when you look in the table, you'll see a different equation for a thick rod versus a thin rod.
Okay.
So we're doing the thin rod approximation. So dm is just lambda dx, right? Otherwise, you have to have two dimensions in your integral.
Right.
All right. So let's do this.
So it's the integral from L minus D to L.
A little bit different, but you kind of hit on the thing, or on a problem. You really need to have two integrals here. One going off to the left side, one going off to the right side.
Okay, so then it'd be from 0 to L, and from D to 0.
So, and I say you have to have two. You can do one. What is? Let's just do it with one. It feels better for me to do it in two because then I don't have any confusion. One is going from here to here, and one's going from here to here.
Right. But
I think we'll get the same thing with one as well. So let's first say, what is my R perpendicular? X is measured from, well, yeah.
X is measured parallel to the rock, isn't it?
Let's just measure X from here and do it in two. Let's measure X like that. So we're measuring X from my axis of symmetry.
Okay.
So in that case, what are the limits of X going from here to here?
D.
D, right? It's going from 0 to D. And notice I went from 0 to plus D. I went from 0 to plus D because all I care about is the distance from the axis. And then I'm going to have
0.
my R perpendicular, because I'm measuring from here, my R perpendicular is just X. That's why I'm measuring from that symmetry axis.
How is your R perpendicular just X?
Because if I'm measuring from, that's X equals 0, then if I go out here, my distance perpendicular is whatever that X is. Right, if my origin is at the axis of rotation, then my X perpendicular is just how far I am from the origin. Because we're one dimensional.
Yeah.
And so I have R perpendicular squared, X squared times lambda dx, right? But that's only counting for this portion. So I have plus integral from 0 to, what's the limit if I go this direction?
L minus D.
And once again, my R perpendicular is X squared.
So lambdas are constant right in front.
Integral of X squared dx, what's that?
X cubed over 3.
Whoops. And this one's just the same. Now, what's the difference between going from minus d to plus L minus d.
From minus D?
Yeah, if I had done an integral that went from minus d all the way to L minus d, if I had done that for my limits of integration, had one integral,
I don't know.
well, what I would have had I would have had this term would have a negative sign and the limit would be a negative.
Right.
And because it's x cubed,
That would
the negative, and it would give me the same answer.
Right.
So it would have worked with one integral. I just feel a lot more comfortable breaking up into two.
Okay.
It feels simpler to me.
All right.
So now putting in my limits, that's lambda. All of them have lambda over 3. D cubed minus L minus D quantity, or plus L minus D quantity cubed. Right?
Yep.
I hope I didn't make mistakes.
And I'm sure you can break it down, well, expand it further. But why would you?
Oh, you could do this in your head too, I'm sure.
I could not.
I misplaced so many. This
Then we are gonna, what is it, Pascal's triangle?
I have no clue what you're talking about.
All right.
What about Pascal?
So if I will do that too. That's a different tangent, but it's just a skill that's useful in science classes and math classes. I think it's Pascal's triangle, and it could be somebody else, Euler's. I don't know. I think it's Pascal's. Okay, so if we add these together, notice d cubed minus d cubed. Woo, those subtract out. And so this is equal to lambda over 3 times L cubed plus 3LD times D minus L.
Like, what? Huh?
I thought those canceled for a second.
Well, yeah. One's L squared D and one's LD squared. Okay, so there we have it about some arbitrary position D. The moment of inertia changes with D.
Yeah, that makes sense.
If D was 0, that'd be if we're going about the end, then we would have just lambda L cubed over 3. Okay. Oh, yes, that's right, because I was like, I have the wrong units. But lambda is mass over length, so it is the right units. In fact, I should write it like this, and then we can cancel.
That was probably cancel 3 if you did something fancy too.
That's a square. That's the simplest way to write it. So if D is 0, then it's going to be ML cubed or ML squared over 3. And if D is equal to L, it's also going to be ML squared over 3. If D is 1/2 L, then you're going to have the smallest possible value, or the smallest?
Well,
Yeah, the smallest possible value of D is 1/2 L. So it gets smaller as you go toward the center, which makes sense because your radius, your maximum radius is getting smaller as you move toward the center. The center, you have the smallest maximum radius. Did you have a question, Oksana?
Well, I'm just trying to think. You said if D equals L, then you just plug in.
If D equals L, then D minus L is 0. The second term vanishes. Okay, the thing I was talking about. 1. Now you take an imaginary 0 and imaginary 0 here, and underneath the separation between any two numbers, you write the sum of the two above it.
Right.
So 0 and 1 is 1. 1 and 0, 1. Now I'll put my imaginary zeros outside again
That's perfect.
and repeat.
1, 2, 1, more imaginary zeros.
And I'll just do, this will be my last line. Now, why is this useful to you?
That's a great question.
Getting rid of my imaginary zeros now. Why this is useful to you is if you have
Wait, how did you?
a plus b raised to the nth power, you just take the row that corresponds with n. So this would be n equals 1, n equals 2. And this gives you the coefficients of the terms. So if I had, for instance, a plus b raised to the 4th power, this is the n equals 4 line.
So it'd be a to the fourth.
It'd be a to the 4th times 1 plus 4 a to the 3rd b plus 6 a squared b squared.
Plus 4 a b to the 4th. Plus
Third.
Third, yes, plus b to the 4th.
That's why it's useful. That's why I could do it in my head.
That is, yeah, okay. That's cool. I like that.
So
It's
it's,
a lot better than writing out 3 different group. Well, in this case, 4 different groups.
yeah, it would have been a real pain to write that out and do all the work.
Wow.
I'm gonna take the picture.
Maybe I got taught that a long time ago, but I do not remember.
All right, going back to topic. I mean, sometimes you have to. All right, find the moment of inertia of a uniform plate. And we're going to do it about the axis shown. Why is this more difficult than what we just did? Well, it's going to be of negligible thickness, so too.
It's going to be a what?
Negligible thickness, so it'll be 2 dimensions.
Okay.
Well, you don't have distances, right?
No, we do. We have what? Wait, what?
Actually, even if it was not negligible thickness, this case here would still be 2 dimensional.
Yes, that's true, because it would be a plane taken out area.
So this is 2-dimensional. So what we're going to have is, remember, dm was equal to rho dv.
Which is lambda.
Now we're going to write this as equal to sigma dA, where sigma is the mass per unit area.
What?
Because this has a uniform thickness, we basically are taking the volume, and with the constant thickness, we divided that out. So we're going to have sigma is m over a, and our dm is sigma dA. In 2 dimensions, I have a dx and a dy. So we'd have like, here's x, here's y. My x and y always. And so my dA is equal to dx dy. A little square out here with dx on one side and dy on the other has area dx dy. Now we're ready to go. Except for we've identified one thing. We have to identify 2 things. We have to identify what dm is. What else do I have to identify? Our perpendicular.
Yes.
If I'm at some random x, y, what is our perpendicular?
Why?
No.
It's square root of x.
Pythagorean theorem.
Yeah, that one.
Let's make life easier. What's our perpendicular squared equal to?
X squared.
Yeah. Since that's what comes into our equation, it's easiest to just do the r perpendicular squared, Pythagorean theorem. Now I can do my calculation. And this would be technically IZZ. It's the moment of inertia about the z-axis, right? Because it's perpendicular to the x and the y. Z is the direction perpendicular to x and y. All right, I have integral, double integral because I have an x and a y. And then I need to put my limits. What are my limits?
Your limit for y would be
0 to L and then 0 to
0 minus w. Or, no.
Whoops, what happened?
dy would be
That was weird.
0 to L.
Okay, I'm changing colors for my variables so that we
0
can
to
keep
0
them
to
separated in our heads, except for the last one didn't come back. Okay, so the greens are going to represent the y, and then I just left everything else the original color.
Okay, so.
So what are the limits on y according to this picture?
L. 0 to L.
Well, the y has a total width of
Well, why
w
did you label that X and the other one Y?
because we have to define what x and y are.
No, it makes sense. So the limits would be 0 minus half of W, I'm assuming,
Okay, so minus w over 2,
and then
2. What's the upper limit?
Why did you divide it by 2?
Because we're going from the axis. So my 0 is right here.
which it looks like that's approximately halfway through.
Yeah, it's supposed to be exactly halfway. It's the center,
So
right? Center of the
then
plate.
it would be 2 W over 2, wouldn't it?
Right. What about the limits for y or x?
Negative L over 2 to L over 2.
Yes. Suddenly I thought that maybe I had my x and y backward in my head, and I was like, it's not going to matter in the end result, but it's, you want to do it right. So now we have to do a double integral. This is a good double integral. It's what we call uncoupled. You don't have the x depending on y. So when I do this, I can do the integral pretty straightforward. I will first do the yellow integral. And so for the yellow integral, I'm just going to leave my limit here and my dy here, and then do the yellow integral. And I know my y is going to turn out to be yellow in here, but
So it would be sigma times, because sigma is constant.
okay, bring the sigma out, yeah.
So sigma times x cubed over 3.
Okay, so there,
Oh, okay, I see.
and then I have to put in my limits.
Yeah.
So there I did the first integral inside the other integral.
And now you take the integral of that with respect to y.
Well, I got to put my limits in first. Otherwise, I'm going to get confused.
Oh, okay, I see what you're saying.
Changing to a different color.
So then we got L over 2 cubed over 3 plus
And
y squared L over 2 minus. Can we change that to plus and just put L over 2 instead of minus L over?
I could, but I'm not gonna.
Okay.
I could, but I'm not gonna, because then if somebody looks at it, they'll say, "Why did you do that?" And well, because minus and a minus is why, but it looks a little less obvious when somebody's just looking at it. So now you do notice, as he said, minus and the cube of a negative is still negative. So minus and minus makes it plus, minus and minus makes it plus. They're both added. I'm just going to put a 2 out front. How's that? No, I won't. L over 2 cubed is L cubed over 8. Multiply that by 2. L cubed over 4. 4 times 3 is 12.
Wait, where's the 4? What? How'd you get the 12 again?
How to get which one?
The 12?
There was the 3 right.
Okay, so L cubed.
This 3 here.
Yeah. L cubed over 2. Okay, L over
L-
2 cubed is L cubed over
8. And then I had 2 of them because the upper and lower limits.
Oh,
And so that made L cubed
okay,
over 4, and then 4 times 3. Okay, so now we're down to the end. Oops, that highlighter's not going to cut it. So now I do these integrals again, and it's going to be
Sigma L cubed Y plus Y cubed over 3.
okay. So when we do that, we're going to have, and yeah, I know I'm out of time. I'm sorry, I put the upper and lower limits for the first term. It's just a faster way. L over 3 times W over 2 cubed minus W over 2.
So that's also going to end up with.
And so these are doubling again. And so that's sigma L cubed W over 12 plus sigma L W cubed over 12. And then because we're out of time, I'm not going to go further with the simplification, but sigma is the mass over area, and so you calculate the area, and you can factor out an LW from each term, and it simplifies even more after you do that. But this brings us to the end of what's calculus. Everything else is algebra, and I'm 3 minutes over. So that ends today. When will I see you next? I'm going with him, Randy. 2.
I wish it was tomorrow.
Well, I personally